Hey Phys 1 kids, Campbell here. In our first video on the unit on forces, we're going to talk about what forces are, what types are there, and how do we visualize them. Well, what a force is just a push or a pull. Simple as that. They cause changes in motion, and they act on objects. Any object. Forces act on you all the time. Now, all forces have an agent, something that causes the force. Right? There's no mystery forces that occur out of nowhere. There's always something has to cause the force, which means we can identify it. Now, there are two types, contact or long range, and I'm going to talk in more detail about that on the next slide. Force is a vector, which means it has both magnitude and direction. It also means, just like in 2D motion, we're going to have to separate what's going on in the x direction from what's going on in the y direction if I have a force that's at an angle. The SI unit of force is the Newton, named after Sir Isaac Newton. And if we want to break it into smaller units, it's a kilogram per meter over second squared. And we're going to see that why that is when we get to Newton's second law, which is several videos from now. Now, the difference between a contact and a non-contact force is just that. A contact force physically touches you. So if I push you, I am touching you, right? So that's a contact force. So anytime there's contact between objects, those forces are contact forces. Long-range forces, also called non-contact forces, are ones that act on an object without physically pulling on them. So, for example, I take my pencil here and I drop it. Well, a force must have acted on this pencil because it fell, but I didn't, and we know that that force is because the acceleration due to gravity from the Earth, but the Earth doesn't physically reach it and pull it down, right? So that's a long-range force, one that doesn't involve actual contact. In fact, we're going to talk about the types of forces, and the first one we're going to talk about is the only non-contact force we're going to be concerned with in this unit. There are other ones, electrostatic forces, which we'll talk about at the end of second semester, and magnetic forces, which you won't learn about unless you take AP Physics 2. So the one that we do work with in this unit and this year is the force of gravity. And the force of gravity acts on all objects that have mass. So pretty much everything we do, always force of gravity. Now, the symbol for the force of gravity is F sub g. You could also write it as F sub little g, but never write it as just g. So F sub g. What the equation for the acceleration, or the force of gravity is, it's the mass of the object times the acceleration due to gravity at that point. So here on Earth, we're going to use 9.8 because we're here on Earth. The force of gravity is also called weight. So when we talk about, how much you weigh, you're really talking about the force of gravity on you. You're not really talking about your mass, because mass and weight are not the same thing. Mass makes up the force of gravity, but your weight depends upon where you're located, what the acceleration due to gravity is on you at that spot. So if you go to another planet, you're going to have a different weight. Now, the vector direction is always towards the center of the Earth. It's always straight down. Right? It's always towards the center of the Earth. So when we draw the force vector for the force of gravity, it's always going to point straight down. So if I talk about mass and weight, let's take a look at how we would calculate the weight of a 10 kilogram block, or the force of gravity on that block. So all we do is we take our 10 kilograms, our mass, and we multiply by the acceleration due to gravity here on Earth, 9.8. Now notice when we do that, we don't put in negative 9.8. You're using the value of g, 9.8. The negative comes in the fact that the force points straight down. So when we do a force calculation, we're going to take into account that the force is down with a negative F sub g. But don't put the negative in here into your 9.8, because if you do that, then you're going to cancel out the force direction. And remember that in physics, negatives and positives are about direction. So positive 9.8 when I'm calculating the weight. Now, would the weight of this block be the same if it was on the moon? Well, believe it or not, the acceleration due to gravity on the moon is a lot less than here on Earth. And we'll talk more about that when we get to our gravitation unit. But so it would not be the same. But what about the mass? Would the mass of the block be the same on the moon? Well, of course, Mrs. Campbell. Yes, it's still 10 kilograms. 10 kilograms is the property of the system. It doesn't change because we go to outer space, but the weight does because that's a force. There are other types of forces. There's a spring force. Now, a spring force could push or pull. So the direction of the vector really depends. So here I have a spring on a little rubber ducky, right? And the spring can pull the rubber ducky, but it can also, if I can get the spring to cooperate, it can also push the rubber ducky. So it could pull it and it could push it. So spring forces could push or pull. Now, the symbol for spring force is F sub S. It is a contact force, that's supposed to be an S. And it does have an equation. The equation for it is negative K delta X. The negative is because it's always in the opposite direction of the change in displacement. We'll talk more about that some other time. So now, like I said, the direction of the force depends upon what I'm doing with my spring. A spring has a happy place, and I like to call that its equilibrium position. So that's this right here in the center. The equilibrium position is the position the spring is in when it hasn't been stretched or compressed. So it's in, like I said, it's in its little happy spot. And so if I stretch the spring, I can feel the spring pulling on the ducky. So a stretch spring exerts a pulling force, and that force direction will point towards the happy place of the spring, that delta X when it was here. If I compress the spring, I can feel the spring pushing against me. A compressed spring will exert a pushing force. So the vector of the force will point in the direction. So if I stretch it, the spring wants to get back to its happy spot because it's extended past where its happy spot is. So the force is going to be in the direction that returns it to that spot, so that way. And if I compress my spring, if I squeeze it in, then it's lost some of that displacement from its happy spot, so it pushes out back to get back to that equilibrium position. So the direction of the spring force, that vector, will always point in the direction of its happy spot. So a stretch spring will point in and a compressed spring will point out. So it's trying to get back to equilibrium. Another type of force is a tension force. So anytime we have something like a rope or a cord or something, that's a tension force. We call it a pulling force because I can only pull this container. I can't push it, right? If I try to push it, the rope goes slack. So tension forces only exert pulling forces. The symbol we use for tension, you can use a capital T, you can use an F sub T. I usually use F sub T, but the vector always points in the direction of the rope. So when I pull up on this container, the vector points up along the rope, so up in this case. With this guy pulling on this stack of weights, which I call the tire, but it really looks like a stack of weights, the force on the stack of tires, or the stack of weights of the tire, is away from it along the rope. But of course, if we were talking about the tension on the man's arms, right, then that tension force would be along the rope in the opposite direction. So it depends upon what we're talking about. What force? Are we talking about the force on the weights or the force on the man? Because then the direction changes. But it always points along the direction of the rope. Now, there is no equation for tension force. It just comes from when we put together force equations. So there's no magic formula. Another force is a normal force, and normal forces only exist when an object is in contact with the surface. So for example, I have this book, my physics book here, sitting on the table. It's on a surface, the tabletop, so it has a normal force. But if I lift it off the table, now it's not in contact with the surface. Well, okay, my hand, but we're not going to count that. So there is no normal force. So it has to be on some sort of surface in order to exert a normal force. Now, a normal force always is perpendicular to the surface of an object. So, the surface that the object is on, not the object itself, but always perpendicular to the surface that's applying that force. Now, your book symbolizes it with a little n. I don't use a little n. I mean, if I use an n, it would probably be a capital. Ooh, I don't know what that tail is. It'd be a capital N. Or I use F sub n. More frequently, I probably use F sub capital N. But something that says it's force normal force. So if we draw it, again, perpendicular to the surface. So the normal force is here, and it points straight up because this surface is parallel to the horizontal here. But if I put something on an incline, now that force is going to rotate. It's going to rotate because it has to stay perpendicular to the surface, and the surface now is at an angle. So normal forces always have to be perpendicular to the surface, not the object. So we're not going to draw a normal force straight up on this one because the surface is this way. So perpendicular to a surface. The last type of force is a friction force. And when I do friction forces, if I don't know, there's two types. And if I don't know what type, then I just write F sub F, friction force. But there are two types. One is static friction. Now, static friction, you'll know, notice the symbol is F sub S, which is also spring force. So you have to be careful. Usually when I write a static frictional force, I'll use like an italicized S, something that's smaller than the spring force, which I use a capital F sub S. But a static frictional force is a force that keeps an object from moving. So, for example, if we go back, actually, let's put my calculator on my book here. If I apply a force to this, it doesn't move yet, but I am applying a force. I can feel it. I can feel my finger pushing. So right now, static friction is working to keep this object from moving. But if I push hard enough, right, then it starts to move. And once it starts to move, then I have kinetic friction. Kinetic friction, we symbolize that with an F sub K. So the frictional force, it depends. Is an object moving or not? If it's not, and there's a force being applied to it, then there's a static frictional force. So for example, right now, I'm not applying a force to this calculator, so there's no static frictional force. But as soon as I start to apply a force, and it's not moving, then static friction starts to come into play. Same thing if I put this on an incline. All right, if I raise this book up, notice it doesn't start sliding right away. That's because there's a static frictional force, but there's a maximum where I overcome that and it starts to move and I have kinetic friction. Now, there are equations for static and kinetic friction, but we're not going to talk about them in this video. That's going to be a whole separate video when we talk about friction. But you do need to know that the vector for friction always points opposite to the direction of motion, or in the case of static friction, in the direction that's opposite of the way the object would move. So, for example, when I am applying a force to this calculator, I'm applying a force this way. So the static frictional force must be opposing that in the opposite direction. So with static friction, I think, okay, what way would this object move with the forces on it? And then the static friction is opposite of that. All right, let's talk about visualizing forces. We visualize forces by what's called a free body diagram, or FBD. A free body diagram is a diagram that shows all the forces acting on an object. I will tell you it is extremely hard to solve a force problem if you do not draw a free body diagram, because there are no magic formulas for forces, for net forces. We have to write our own formulas. So we need a picture to see how are the forces pointing on this object so I can write my equation correctly. Now, the steps to drawing a free body diagram: one, you draw the object of interest or the system of interest as a dot or a box. So no fancy pictures. If it's a car, don't draw a car, dot or box. You go through and identify all the forces. Is there a force of gravity? Absolutely. All objects will have a force of gravity in its free body diagram. Is there a spring? Then we have a spring force. Is there a rope? Then there's a tension force. Is it on a surface? Is there a normal force? Is there friction? So we identify all of the objects and then we draw vectors in the direction of those forces. So force of gravity would be down. Tension would be along a string, away from the object of interest. Spring force, it depends if the spring is compressed or stretched. But we draw vectors, and this is very important. The tail of the vector must touch the dot or box, whatever you drew. Must touch, and it must point away from the object. In your engineering classes, you may draw vectors that point towards the object. So the arrowheads are pointing towards. Don't do that in physics. They point away. College Board